Okay, so today we're going to talk about the current voltage characteristics in a circuit. So what does this mean? Well, this is basically us saying for a certain component, as I vary the voltage across it, how does the current behave? So what we ideally want to come up with is a graph which shows if I increase the voltage, what does the current do? And different components behave in different ways. So first thing we're going to talk about is how do I vary voltage across a component? Well, I've got a fairly simple circuit drawn out here. And if we look at what we've got here, we've got a battery in series with a resistor, a bulb, and I've got a voltmeter across that bulb and an ammeter. So this circuit is all well and good. It would allow me to measure the voltage and the current for whatever the voltage of that, whatever that voltage is. But what I really need is to be able to change that voltage and look at that relationship in order to plot the graph. So what could I do? Well, given I've got a resistor in this circuit, one thing we might want to do is to make that a variable resistor. So that would allow me to change the voltage across that bulb as they share that voltage. So that's all well and good. The problem is this will not allow me to get a full range of voltages. So if we think about this circuit, this bulb and this resistor are going to share that voltage. This bulb will never have 0 volts. It's always going to take a certain fraction of that voltage because it has resistance. So what I want is a way to get a full range of voltages from 0 up to some maximum value. So this circuit won't work for that. Another alternative could be to use what we call a variable power supply, which is represented like that. Now this would work, but these are not always available. So instead, what I'm going to give you is an alternative way of varying the power supply using a clever setup and a new component which I'm going to introduce to you now. So that component is called a potentiometer, and this is what it looks like. So the symbol for it is shown here. It's basically looks like a resistor, but it's got this extra leg on the bottom here with an arrow pointing inwards. So what this actually looks like, well, you might have seen these in school. So we often call this design of potentiometer a rheostat. We normally use this as a variable resistor, just connecting up 2 legs. What you might have noticed as you play around with these things is that it's actually got 3 legs. 1, 2, and 3. And this 3rd leg allows it to give you a clever setup in a circuit to vary the voltage across something. This design you might have seen in things like guitars or in various simple circuits. This is what you might look like if you order one off the internet. So why is this useful? Well, I've got a little setup here. This 3rd leg, this allows us, this can be slid all the way along from here up to here. So this can be moved. If I slide this all the way over to the left-hand side, what does that mean? So if that's going to give us this situation here on the left in black. So this leg has been slid all the way over to the left-hand side. So we've essentially got my bulb in parallel with the full resistance of that potentiometer. So I've drawn an equivalent circuit here on the right, shown in blue. So basically, if I have a certain voltage V in here, the voltage across this bulb will also be V in. What about the other hand? If I slide this all the way to the other side now, all the way over to the right-hand side. Well, let's take a little look at what this circuit instead looks like. So this is what the circuit looks like in black. That movable leg's been moved all the way over to the right-hand side. If I compare the circuit here now, I've got this resistor in series with the bulb and this short circuit here. So what's actually going to happen is all that current's going to flow through that loop there, and so 0 voltage is actually going to be across the bulb. So in setting up my circuit like this, I allow the voltage to be varied. Voltage across the bulb can be varied from 0 volts up to V max, whatever that might be, V in. So I've got a full range of readings, so I can get a full set of current voltage characteristics. So what does this actually look like in a circuit? Well, let's have a little look now. On the left, I've got my circuit diagram for how I might investigate current voltage characteristics of a filament bulb here. So I've got my potentiometer here, I've got my filament bulb here, and then I've got my voltmeter and ammeter connected appropriately across the bulb. I've set this up here on the right-hand side, and I've got a little photo to illustrate what this actually looks like. If I just take a little look at this picture here, I've got my potentiometer connected up to my battery there, so that's this bit here. From there, I've got this yellow wire, which connects directly back to the bulb. That's this one here. And then this other black wire is in series with a bulb. The voltmeter is connected up using those green wires. If I keep following that round, it's then connected up to an ammeter, which goes back to my bulb. So that's this part of the circuit here. So this should allow me to investigate the current voltage characteristics of my bulb or different components. So there are three components you need to understand a bit about the current voltage characteristics. So the first one is a fixed resistor here. So fixed resistors are often used in electrical circuits. The resistance values are given by the colours of these bands. So this one here is brown, black, red, and that will correspond to a certain value. So let's say, for example, this is 50 kilo ohms. Okay, well, what does that look like on a graph? Well, a fixed resistor is what we call an ohmic conductor. So basically what that means, it's got a directly proportional relationship. Can't spell. So if it's directly proportional, what does that actually mean? Well, that means we're going to have a straight line through the origin like so. And that's characteristic of a ohmic conductor. So given this relationship, how could I find the resistance? Well, we know Ohm's law is given by V equals IR. If I rearrange that, I'm going to end up with R equals V divided by I. Okay, so for this circuit, how could I find the resistance? Well, if I pick a certain voltage, go up and across, I'm going to have a certain voltage here and a certain current, and my resistance will be given by V divided by I. Okay, so mathematically this would be the same as 1 divided by the gradient. Well, let's change my resistance here. If I've got a bigger resistor here, so in red there we did a small resistance. If I increase the resistance, well, what's that going to look like? So let's pick this same voltage that we looked at before. If I've got the same voltage and I've got a bigger resistor, does that mean I'm going to have a larger or smaller current? Well, if there's a bigger resistance, that current is going to be smaller. So what will that look like? It means for that same voltage, I'm going to have a much smaller current flowing. So this is a higher resistance. So we can see here, the shallower the line, the higher the resistance. Okay, and I mentioned previously, the resistance will be given by 1 divided by the gradient, but it's important to mention that that only works because I've got this straight line relationship here. That will not apply for other components later on, and I'll talk about that in a second. Okay, so that's the first one, the fixed resistor. Moving on, the next one we're going to talk about is a filament bulb. So, symbol here on the left, I'm sure you've all seen this one before, and a filament bulb is kind of your traditional light bulb, and these are obviously going out of fashion now with more energy efficient means, but what this basically is a little filament in here, which is a very thin piece of wire, and as current passes through it, it gets very hot, and as it gets hot, it emits light. That's the simple principle of how these things work. Now, importantly, what we've got to know is that a filament bulb is non-ohmic. So a non-ohmic conductor basically means we don't have this directly proportional relationship. So we don't have that directly proportional relationship between current and voltage. And we're going to talk a bit about why that is. So, for a bulb, well, this is what the relationship looks like. Initially, as I increase my voltage, I get an increase in current. But as that voltage gets higher, this flattens out a bit. If I go negative and I put the current through the other way, we get the exact same thing but reversed. So I sort of get this sigmoidal relationship as I increase the voltage. So what does this actually mean? Well, let's break this up into a few parts. So here, I increase the voltage by a certain amount, and I get quite a large increase in current. So if I get a large increase in current, that means it's got a fairly low resistance. As let's say that was 1 volt. If I go the same amount up again, 2 volts here. And here I get, if I double the voltage there, I have not doubled the current. So it's no longer directly proportional. Well, what does this mean? It means that because I get less current increase, my resistance has gone up. Let's go again to 3 volts. And I get an even smaller increase in current. So what's actually happening is as voltage increases, the resistance is increasing. So why is that? Why is the resistance changing with my voltage? So the key thing here is understanding the principle of how a filament bulb works. It works because that wire gets hot. So let's think about what's actually happening. So in order for something to conduct, my electron, shown here in red, has to pass from one end to the other. As it moves through, it collides with the metal ions, shown here in blue, within that wire. So these metal atoms are going to be vibrating slightly, as all solid atoms do. Okay, so let's have a little think. As this wire gets hotter, what's going to happen to those metal atoms? Well, they're going to vibrate much more vigorously. So all these metal atoms are jiggling around, and this electron's trying to get from one end to the other. So if you're trying to imagine you're pushing through a busy crowd, if that crowd's bustling around a lot more, you're going to find it much harder to get from one end to the other. And it's the exact same thing here. So as temperature increases, what happens? Well, the metal ions vibrate more. Vibrate more quickly. And this means that there's more frequent collisions between the electron and the metal ions. And this means we get a higher resistance. Okay, so that's the explanation there. So why do we have this curve? Well, down here we've got a low resistance because it's cold. Up here we've got much higher resistance because it's hot. So this non-ohmic relationship is all because the bulb temperature increases, the filament temperature increases. Okay, the final component we need to understand a bit about is something called a diode. So this is a symbol for it. Basically, what a diode is, the way I like to think about it is it's a one-way street for current, or a little valve. So this, if you put this in a circuit, it basically stops current flowing the wrong direction. Perhaps you're trying to protect a delicate part of a microchip or something like that. Really useful in different circuits. Over here, this is what they actually look like. We can see the silver end here. Basically, this is so you connect it the right way around in a circuit. Over here, this is something called an LED. So it's exactly the same thing. Circuit symbol looks like this, but it gives out light, which we represent with those arrows. Both of these things will stop current flowing in one particular direction. Okay, well, let's look at the current voltage characteristics for a diode. So because this stops current flowing in the wrong direction, well, that means that if we have a positive voltage or a negative voltage is going to be important. It's not going to be symmetrical. So if we put a positive voltage across it, this is what we call the forward bias. So we can think of that as the right way down the one-way street. The other one, if I go backwards, well, that's me going against the flow. That's called reverse bias. Okay, well, let's look at forward bias first. Well, we know that my diode allows current to flow the right direction. So as I increase my voltage, I'll get an increase in current. Okay, so it looks a bit like this. And because it's got very low resistance in the forward bias, I have a very steep line. Now, you might have noticed this did not start increasing from the origin. I had to put a certain voltage across it before my diode actually allowed current to flow. And this is characteristic of semiconductor materials. Now, the value is basically 0.7 volts, and that's kind of characteristic of a silicon-based semiconductor. So basically, the way I like to think about this, if this was a valve in a pipe, I need to apply a certain amount of forward pressure before that valve opens and allows the current to flow. So it's like it's what we call the switch on voltage. So it's the voltage I need to apply before this thing starts working and letting the current through. Okay, so let's look in the reverse bias now. So I'm basically now trying to push current the wrong direction around the circuit. So I'm applying a certain voltage, and you might even get a little bit of current leaking through. So this is not completely at zero because I'm pushing voltage the wrong way around and a little bit might get through. So you might get a little bit of diode leakage. So this is basically the diode working as it should. It's stopping that current flowing. However, if you think back to that valve analogy, I've got this water flow, and I'm trying to push water back against this valve, which is stopping that flow. Think about what happens if I keep increasing that water pressure the wrong direction. Well, eventually, that valve's going to give. And it's exactly the same thing that we have in this electrical circuit here. Eventually, if I keep increasing that backwards pressure, I'm going to have a certain breakdown voltage, at which point the current starts to flow in the opposite direction. So this is the current voltage characteristics for a diode. So those are the three you need to know about. An ohmic conductor, so this could be a filament, this would be a fixed resistor, or it could even be a normal piece of copper wire for a certain range of temperatures. A filament bulb, on the other hand, that's a non-ohmic conductor, and we have that characteristic sigmoidal shape. And finally, a diode's the funny one. It's a silicon-based semiconductor, and this is what the current voltage characteristics look like. Thank you for watching.